All right, chapter 13, assignment 10. We've done resistance circuits, capacitance circuits. We've done resistance capacitance circuits, resistance inductor circuits. So we're missing something critical, and what would that be? Yes, indeed, it is inductor capacitance circuits, usually referred to as LC circuits. Now, an LC circuit is one that has an inductor and a capacitor in it. So I have an inductor and a capacitor. Now the first question on the page is, if I charge the capacitor and then plunked it into this wiring system, what would happen? Well, I'll let you take a moment. I'm hoping you'll figure it out yourself, and then it'll stick for you for life. If not, I will let you know in a second. You pause, but if not, 3, 2, 1. All right, so what happens here? Well, this thing, if you have charge, let's see if I had a pen, there's a pen. So let's say I have pluses up here, minuses over here. Electrons start flowing this way. They try to flow this way around that loop, right? The problem is what happens when they get to the inductor. The inductor has no current traveling through it, so it stops the system. So initially, there's very little current flow. Eventually, though, that current flow starts to increase as the inductor relaxes, as it creates magnetic field lines, makes it easier for the current to come in there. Now, at some point, all of the electrons that need to get over here, and so I have a neutral capacitor. But at that point, the inductor still has magnetic field and wants to have the current keep going. So the inductor would continue to shove more charge in here until the energy level of the capacitor reached what it was before, essentially switching which one's negative and which one's positive. Then the inductor would be completely shut down because it's used up all its energy and can't resist change anymore. But now I have a charge, this side of the capacitor is negatively charged and that side is positively charged, so it would start running the other way. So this thing oscillates. Things that oscillate, in physics land we know the period is going to be 2 pi square root of things that slow it down divided by things that speed it up. I know you can't read that, so I don't know why I'm writing it, but whatever. Things that slow it down versus things that speed up. Now, a really large capacitor with a large amount of capacitance can carry an awful lot of charge and fairly low voltage. So because of that, it's going to be pretty slow to dispense its charge. Likewise, an inductor that's resisting change, the more coils, the bigger the inductor, the more it's going to resist the change. That's what they do. So in this case, my period formula becomes 2 pi, inductors slow it down, and capacitors both slow it down. What's interesting about this formula is, well, not interesting, what's from it. This LC is considered the time constant. It is not a time constant, not in the traditional sense, but that's what it is considered if you ever get asked the question. That is the time constant. Does that make sense? In a sort of goofy sort of way. Okay, so now the question is, what else have we got here? Okay, well, we also know, by the way, whenever we're dealing with oscillators, we prefer to deal with energy. So the energy of a inductor is 1/2 Li squared, and then the energy of a capacitor is 1/2 QC, I think. Hold on. It should be QV, so I'm doing something wrong. V is equal to Q over C. So what am I doing wrong here? So it must be Q squared over C? No, that's not it. Hold on a second. Let me think that through. Yeah, it's Q squared over C. Well, things you learn. Okay, so it's going to be, UC is going to be equal to, replacing the V with that, you get 1/2 Q squared over C. Okay. All right, so those are my two energies. So whenever you're dealing with with a capacitor and an inductor, and you want to know something, you may have to use energy to figure that out. Okay, what's the maximum current? That's when all of the energy's in the inductor and none of it's in the capacitor. Capacitor just charged, right? So you could figure out, you know, if I give you what the initial charge of the capacitor was, you could figure out what the inductor's maximum current was, and those sort of things. Or if I give you a certain amount of charge on there, you could figure out how much, whatever the leftover energy would be, 1/2 Li squared, and you could solve for it that way. Okay, so you do it very similar like we did oscillators before. The only thing else that we have to worry about is sometimes we talk about frequency. Frequency is 1 over the period, correct? So you might want to remember that little gem. And I'm trying to think what else you need to have here. I think that just about covers everything you need to do a simple set of these problems. And so let's go ahead and have you do number 1. I'm going to pause it. And sorry, I'm going to ask you to pause your thing, and then we'll do problem number 1. Okay? And then hopefully that'll be enough to get you through the rest of this worksheet once we get that done. So try problem number 1, and then I'll do problem number 1. All right, it's potty time. Again, if you haven't done it yet, please do it, because you're going to be in much better shape if you practice this one of the few times I give you a problem to do so. So I've got a circuit, and the circuit has a capacitor on it and an inductor, and then it comes back. I've got a switch so that I can keep the capacitor charged. Now, before this happens, according to the problem, I'm going to take a 24-volt battery, and I'm attaching it to the capacitor to get the sucker ready to go, right? So that capacitor is going to be CV equals Q, because it says it's fully charged. The capacitance of it is 10 picofarads. That's 10 times 10 to the negative 12th. The voltage of that battery is 24 that I charge it with, so I can get the charge on it. And the charge on that would be 24 times 10 to the negative 12th. Why am I doing that with a calculator? Now I'm embarrassed for both of us. Okay, so that would be 2.4 times 10 to the negative 10th coulombs is my charge. Okay, all right, so that's how much charge I have at the very beginning. Then I take this system away, don't need it anymore. I'm going to put that much charge on this, at this 10 times 10 to the negative 12th farad capacitor. And then I've also got a 0.00063 Henry capacitor. Okay, I'm sorry, Henry inductor. Okay, so now I look at the problem and I go, okay, so question A. If all the resistance circuit is neglected, which we're always going to do in this problem, so that's not really a big thing, but it's, you know, kind of lawyerism. Determine the maximum value of the current in the oscillating circuit. Well, so when I want to find something other than the time it takes, I'm going to go energy, as we do with all oscillating systems. I hope that's a good review for what you need to do. So energy of an inductor is equal to energy. So energy before, let me do this right. Energy before equals energy after, right? So the energy before is the energy of the capacitor plus the energy of the inductor is equal to the energy of the capacitor plus the energy of the inductor. Now, at the very beginning, there's no energy in the inductor. And in fact, the maximum amount of current would be the point where the capacitor no longer has any charge on it. That would be the moment when the inductor is kicking into full speed. So therefore, there'd be none there. So then I'm simply going to go 1/2 Q squared over C equals EL, which is going to be 1/2 Li squared. The rest of this point, hopefully mathematics. Q is 2.4 times 10 to the negative 10th. I'm going to square that. Maybe the energy is going to be negligible, but whatever. 10 times 10 to the negative 12th equals 1/2 Li, which is 0.00063 L. And I want to find the maximum current. So at this point, when the capacitor no longer has any energy, I would have all my energy shoved into my inductor, and so I could do this problem directly like that. So 0.5 times 2.4 to the negative 10th squared divided by 10 to the negative 12th. Boom. times 2 divided by 0.00063 square root, delete square root, boom, and I get that the maximum current would be equal to 3.02 times 10 to the negative third, and current's measured in amps. And I could, by the way, if they gave me how much charge was left on the capacitor, I could use that to figure out what my current is at that time. Using the exact same expression, I just have energy for that expression right there, right? Wouldn't I? All right. B, what's the frequency? Well, period equals 2 pi square root of LC. So the period would be equal to 2 pi square root. L was 0.00063. C is equal to 10 times 10 to the negative 12th. And I'm going to square root that monstrosity, so 0.00063 times 10 to the negative 12th. Boom. That looks like a 6 in there. I do apologize. To the 0.5. Boom. So I've sort of square rooted it. Times 2 times pi. And this thing's going to be cranking through a full cycle. A period is going to be equal to 4.99 times 10 to the negative 7th. That's seconds. The question actually asks, what's the frequency, right? Double checking, yes, is what's the frequency? So I'm going to do 1 divided by shift answer, and I'm going to get my frequency for this thing. Frequency would be equal to 4.99 times 10 to the, oh, that's not right. It's like that makes no sense at all. It's 2, I'm going to put a, 201. I guess I can put a 1 there. 201,000. Nope, my mistake. 2,010,000 hertz. So that's my second answer. 2,010,000 hertz. All right. And the third question, C, what's the maximum energy that you can store in the magnetic field of the inductor? Well, I'm going to go back to my roots. I know the energy before equals energy after, and at the maximum, there's none in my capacitor. So therefore, I could just solve for the energy inside of my capacitor. And that's going to be 1/2 Q squared over C. So my energy would therefore be 1/2 Q, which I solved to be 2.4 times 10 to the negative 10th squared divided by 10 times 10 to the negative 12th. And I'm going to put that on my calculator and get a massively small number. If massively small makes any sense at all. Probably could scroll backwards and find it in my earlier work, but we're just going to do it official-like. Divided by 2, and I get that the max amount of energy that could be, that's in my capacitor at any time, is also the maximum amount in my inductor, and that's going to be 2.88 times 10 to the negative 9th joules. Okay, so that would be how to do that problem, and all the problems are virtually going the same way. Just remember, the key is if I want to know what time something takes, or the frequency of it, I'm going to use period equals 2 pi squared of LC. Anything else is probably an energy problem, and you should do energy before equals energy after, and you're going to be summing up the energy of the capacitor plus the energy of the inductor is equal to energy of the capacitor plus the energy of the inductor. Go ahead and finish up this worksheet. This means we're done with the circuits chapter, which is awful nice. So as such.